I have struggled to understand consciousness for much of my life, and while thinking over how to explain consciousness in physical terms, I realized that you can't explain consciousness separately from its substrate. That is, the organism that embodies it and its biology. So I started a project about life, what is life, and how it came into being. The result is this article, which ended up being much longer than I wanted. In it, first I propose a definition of life, which I call lifeness. Lifeness is just the product of the amount of information that describes something multiplied by the time that it has existed. So it has units of bits and seconds. This is a continuous definition of life. At odds with our binary understanding of life versus death. So, according to it, simpler and shorter lived things have lower liveness than more complex and longer lived things. For example, a hydrogen atom may have existed since the Big Bang, but it's relatively simple, made up of just a few quarks. Whereas a human being is rather complex, but most of its constituting matter is fluctuating. It is eating, its skin is shedding, its gut is sorting out food. So only a subset of it remains unchanged. Second, I also suggest how life may have spontaneously appeared in externally driven non-equilibrium systems, like Bernard cells, and the surface of Earth, whose many ecosystems are externally driven by the sun. The upshot is that, in theory, life could appear spontaneously. Third, I ran a lot of simulations of different interactive particle worlds using a code inspired by the program Particle Life. This is a program that allows you to simulate a world where a few different types of particle interact with each other. The only thing these particles do is attract or repel each other. What I want to demonstrate here is that you can actually find strikingly lifelike behavior here just by having a few different types of particle and by fiddling around with the interaction parameters. Here you can see a number of slides, each of which correspond to the strength of interaction between particles. Cyan is repelled by green, but let's make it negative. Now cyan is attracted by green. And let's make it also for red. So now cyan is also chasing red. But see that although cyan is trying to chase both red and green particles, red and green are repelled by cyan. So the result is this empty halo around these throbbing clusters of cyan particles. The button Random Rules starts a new world with fully random interactions. Let's press it. It seems almost incredible that such richness and complexity can be generated by just having a bunch of particles which attract or repel each other. If you think of these particles of atoms, the rules that govern them are not unlike those that govern the atoms in our physical world. Fourth, I devised a filtering algorithm that takes configurations of particles and fits them on the fly to a hierarchical Gaussian model, which enables to measure liveness at different spatial scales. And after those very many different world simulations, I measured their liveness using this algorithm. So what did I find? One thing is related to criticality, which is a physical concept that indicates an intermediate state between stillness and chaos. In the case of brains, between brain death and epilepsy, precisely the regime in which the brain normally operates. So I found that the worlds that lie closer to criticality contain entities with higher liveness. And liveness is not just a random measure, because things with higher liveness also look more lifelike. And if the definition of liveness is worth anything, then they are also more alive.